We're going to talk about section 2.2, domain and range. So hopefully a lot of this is review. The domain is the set of input values of a function. A lot of times that'll be x, but not exclusively. The range is going to be the set of output values. A lot of times we associate that with y, but it doesn't have to be. Sometimes we restrict the domain of a function because of the context of the problem. For example, if we had a equals pi r squared, where that's supposed to be the area is equal to pi times the radius squared, r is the independent variable acting like x, and so it wouldn't really make sense to have a radius that is negative certainly, and maybe not even 0. So it might be that in the context of this problem, we choose to restrict the domain to just r greater than 0. Once that has been restricted, then that will impact the range, but usually we just kind of let the range work itself out. So here we've restricted the domain there. So if the domain is not specified, we assume that the domain is going to be as large as possible. So that's all real numbers, which we have a very convenient symbol for. It's a double bar r. So that represents all real numbers, the set of all real numbers. So even without the braces, that is a set. So range in general is a little bit more difficult to determine, so we'll be talking about that down the road a little bit. But let's look at these examples here. First, we're going to start with finding domain and range from functions represented by graphs. And then we'll try to look at functions in other forms and see if we can figure out how to find the domain and range. So the domain is going to be the set of x values, or how far right and left does that function go. So it's got a smallest x value of -2, and that open circle means it's not including it, so we'll not quite get up to the -2, and that's going to go all the way to +3, and because of the solid dot, we know that's including the 3. So there is one way of representing our domain, and as we have seen before, you could also do what we call interval notation, and the parentheses means the strict inequality, and the bracket means including that. In the second example, we can see there is a vertical asymptote at x equals 1. So there is no place on the graph at x equals 1. So the domain here is going to be everything except for 1, which we can write as x not equal to 1. Now the range, the y values, if you kind of look at that, you can see that these yellow curves approach the x-axis but never quite reach it. So there is no point on the curve that has a y value of 0, but all of the other y values are taken by some point. Okay? And the third example, now, domain. So if you look at this, there's an open circle there that goes to a closed dot. There's an open circle there, so there is no duplication there. That is, this is truly a function. It's going to pass the vertical line test because a vertical line that comes down the y-axis would intersect the graph at this point, but not at the open circle. So we are going to get for x values all the way up to but not including -1, then all the way through to and including +3. So our domain is going to go from -1 to +3. Now the range can be a little sneaky. Now all of these points in here have a y value of -2. All of these have a y value of -1, but there is no point that has a y value in between -2 and -1. So the only y values that are used by this function are going to be those four values, -2, -1, 0, and 1, and so the range is just those four values. So let's go to a new screen. So next we're going to talk about finding the domain from equations, functions that are given as equations rather than the graphs. So there are, in general, let me back up. In general, the domain is as large as possible. So we assume the domain is going to be all real numbers unless one of these three types of things occurs. So there's three types of functions that have restricted domains. So the first one is something where you have an x in the denominator of a fraction. So the issue here is that we can't have a 0 in the denominator of a fraction or it'll be undefined. And so whatever that denominator is cannot be equal to 0. So that means x cannot be, in this case, -2. And so we would say the domain of f is anything except for -2. On the second one, g of x, functions are what we call real valued functions. So you may have in your Algebra 2 days talked about imaginaries, and we will do that later on in here. But in general, a function has to give us only a real number. So in this case, because we have a radical that has an even index, that is, this is a square root, so the same would apply for a fourth root or a sixth root or any even root. Now a cube root, something like the cube root of x, would have for its domain all real numbers, because there's no problem with taking the cube root of, say, -8, that would just be -2. But when we have an even root, like we do in this square root, this thing inside the radical has to be strictly greater than or equal to 0. So if we solve that, that leads to x being greater than or equal to 5. So that will be the domain of that square root function. Now a logarithm, and I know you guys didn't do a whole lot with this last year in the kind of shortened year with Corona coming in, but a logarithm in general, and we'll talk much more about this down the road, a logarithm in general has a graph that looks something like that. So what happens, you can see, is it is not defined for either negatives or 0. So similar to what we did with the radical, but slightly different, is we're going to say that x minus 2 has to be strictly greater than 0, cannot be or equal to. And so that is going to lead us to a domain that is x greater than 2. So let's look at a few examples that are more challenging. So or let me back up. First, let me talk about range. I didn't mean to skip over that. So let's talk about range a little bit here. Now, for us in AP Prep, most of the time I will let you use your calculator and graph this and try to determine the range from there. But in AP Calculus, eventually, you're going to have to be able to figure it out without using a graphing calculator. So I still might appeal to a graph, but in general, we can see here that with this y equals 1 over x plus 2, we can get any number we like out of this, except for it can't be a 0, because the only way we get 0 is, and a fraction, is if the numerator is 0. And so the range in this case is going to be everything but 0. Now, if you were to graph this, and we'll talk eventually about how to graph this pencil and paper, what you're going to see is something that looks like this. It's going to be above and below the x-axis, but it will never quite touch the x-axis, and that's why you're not able to get a y value of 0. Now, a square root, you may remember, this square root, well, I'm going to talk without referring to the graph first. This symbol, square root, is known as the principal square root, and so it will always be equal to a non-negative number. So I don't say positive because it could also be 0. So if you remember the graph, that might confirm this. that it's going to be translated. It's going to be that kind of half of a sideways parabola translated. But you can also tell without referencing the graph if you know that this square root symbol is never going to be negative, and that's how we're going to get a range that is y greater than or equal to 0. In a logarithm, you can see from the graph here that this will be just translated 2 over, and in fact any logarithm is going to have a range. That is, there is no limit to how high and how low that will go. The range for any logarithm is going to be all real numbers. Okay, I'm going to go to a new screen and we're going to talk about some more challenging domain and range problems. So on the first one, f of x is equal to x squared minus 25. Again, like we talked about on the last panel, this thing that's inside the radical has to be greater than or equal to 0. Now, you cannot mathematically add the 25 and square root both sides with an inequality and get something that is meaningful. So I'm going to insist instead that you factor this thing. And now we're going to look at a number line. And our claim is that this can change from positive to negative or negative to positive only by going through 0. And this will equal 0 at positive 5 and negative 5. So I'm going to put solid dots there because equal to 0 is going to be defined in a square root and will be part of the domain. So now what I'm going to do is I'm going to test each of these 3 regions to see if the product here is positive or not. So if I put in any point over here, and I'm going to take as a representative, say negative 6, if I plug in negative 6 for x, then negative 6 minus 5 is a negative, negative 6 plus 5 is also a negative, and a negative times a negative is a positive that is greater than or equal to 0, which means everything over here is going to be in the domain. Now if I take a representative from the middle region, I can use anything, but 0 is kind of a nice one. Then 0 minus 5 is going to be negative, 0 plus 5 is now positive, and a positive times a negative is negative, which is not greater than or equal to 0, which means there's going to be nothing in the domain in between negative 5 and 5. Taking a representative from the far right region, like say 6, then both of these is now positive. That is greater than or equal to 0, and so this also is going to be in the domain. So the way I say those 2 parts is I'm going to have to get 2 different inequalities here. X is less than or equal to negative 5. I'm going to use the word or, and then x is greater than or equal to positive 5. Okay, there's no way to write that as a double inequality. Let's compare and contrast that with this next one. Another radical. This time I'm going to take the inside of that radical and say it has to be greater than or equal to 0. So again, with these x squareds, I can't just try to get x by itself. Instead, we're going to have to factor that. So I'm going to factor that as 3 plus x, 3 minus x. Again, we're going to do a number line. This will equal 0 at negative 3 and at positive 3. Those will get solid dots because that's included in the domain. And then I'm going to test the regions again. Plugging in, say, a negative 4, this is going to be negative. 3 minus negative 4 will be positive. The product of a negative and a positive is negative, so nothing is in the domain to the left of negative 3. Checking the middle region, I'm going to pick 0. Now 3 plus 0 is positive. 3 minus 0 is positive as well, and the product of a positive and a positive is positive, and so that's going to make everything in between here a solution, which makes that in the domain. And finally, checking the far right region, 3 plus 4 is positive, but 3 minus 4 is now negative, and so a positive times a negative is negative, and so our domain is just the stuff in between negative 3 and 3, which we can write as a double inequality. So the stuff in between can be written in that way. Now, the range is tougher. So let's talk a little bit about this. And I would let you use your graphing calculator. You can also, if you reason your way through it, I'm going to try to make this claim, you can see that the smallest that, I'm going to change colors here, the smallest that this could be is going to be when it's equal to 0, because there's no way a square root can be equal to a negative. If we start taking the square root of a negative, then it's not defined. So the smallest this could be is 0, and that will in fact equal 0 when x is either 5 or negative 5. So for a range, it is going to be equal to 0, but not smaller. Now, this can get bigger and bigger and bigger as x gets bigger, so there is no limit to how large that can be, and so that is going to be our range. Y greater than or equal to 0, or you can write it as 0 less than or equal to y. Now it gets tougher still over here on the next one. Now, the smallest this can be, again, because a radical can't be negative, the smallest is going to be a 0, and that will actually equal 0 when x is equal to 3 or negative 3. So that's the smallest it's going to be. Now, the biggest, here's the reasoning without a graph, the biggest this can be is when we subtract the least amount. So when the x squared is the smallest x squared can be. Now the smallest an x squared can be is 0, because negatives, remember, when you square them, are going to become positive. So the smallest, so let me back up. The biggest 9 minus x squared can be is when x squared is the smallest, and that's going to be when x is 0, which is going to make y the square root of 9, which is going to be 3. So without looking at a graph, and this is tricky, this is something I would expect AP Calculus students to be able to do, not for you at this point. Y would be between 0 and 3. Now, if you graph this on your graphing calculator, you have to be a little careful because it's not always very clear what happens right in these areas here. But what you should be seeing, what your calculator is trying to show you, is a semicircle. But sometimes it looks like it stops short of the x-axis. And we'll talk in class about how to use our calculator to identify what that is. Okay, let me go to a new screen and I'll show you a new example. This is another tough one here. Let's say that h of x is equal to the square root of x minus 2 over x plus 3. So once again, I'm going to refer to a number line here. Now, again, this is only going to be defined when what's inside this square root is positive. So what's inside the square root will be positive when either the numerator and denominator are both positive, or when the numerator and denominator are both negative, making the quotient positive. So the idea is that this can change sign either when the numerator is 0, which is going to be at positive 2, or when the denominator is 0, which is going to be at negative 3. Now, when x is equal to positive 2, that's going to make the numerator 0, and 0 divided by anything is 0. The square root of 0 is defined, so that's going to be a solid dot. But when x is negative 3, the denominator is 0, which is undefined, and that means we're going to put an open circle at negative 3. Now, like we've seen with the radicals, we're going to test each of these regions to see if the result is positive. So if I put in, say, a negative 4, then a negative 4 minus 2 is going to be positive in the numerator, but a negative 4 plus 3 will be negative in the denominator. A positive divided by a negative is negative, so that's not going to be in our domain. If I plug in something like, say, 0, then we'll get a negative numerator and a positive. Did I do that right? Oh, back up. I think I did that wrong. Let me back up to this one. So if I plugged in a negative 4, then the numerator, I did that wrong, sorry. Then both the numerator and denominator are negative. There we go. And that's going to make a negative divided by a negative a positive, which is going to be in then the domain. Because then when we plug in 0, we're going to get a negative over a positive, and that's not in the domain. And when we plug in something bigger than 2, like say 5, then we're going to get a positive over a positive, and that'll be in the domain. And we'll get this kind of split domain again, which is going to be x strictly less than negative 3 or x greater than or equal to 2. And I'm not going to ask you a range on this one, so we'll just live with that. Okay, very good. Hopefully this will help you with homework number 10.